Hello everyone and welcome to our 19th lecture, Statistics. By the end of this lecture you will know what things like mean, variance, standard deviation, distributions, t-test, q-test, or whatever are. Not all of them, but a few. So why statistics? Because they help us summarize data, detect patterns, evaluate uncertainty, decide whether differences are real or random, and predict outcomes. We can separate types of data into two groups. First are quantitative, which are measurable values, stuff like mass, time, count, concentration, and qualitative, which are categories like color change or pass or fail, results, etc. So quantitative means you get a certain numerical value, and qualitative is as observed change, so color change or true-false switches. In chemistry, we have quantitative and qualitative analysis. The qualitative tells us which compounds are present based on the color changes or whatever other tests we do, while quantitative analysis tells us how much of each compound is in our sample. So today we'll focus mostly on quantitative data and what we can do with it. So the first thing is central tendency. It is a summary statistic that represents the center or a typical value of a dataset. Most common measures for it are mean, or arithmetic average, median, or the middle value, in the set in ascending order, and mode, or the most frequent value. So let's see more about each on a specific example. Let's say we have a group of kids with different ages. They are 4, 5, 6, 12, and 13. So we order the list from the lowest to the highest value. And then for our mean, or the average, is obtained when you add all the values together. So you remember this symbol sigma here. I means for I equals 1 means that we start with the first number in the set. And then n means the last one. And xi means that we add elements xi. So we add x1 to x2 to x3 all the way up to xn. So x1, x2, x3, x4, x5. And then we divide by the amount of them. So this symbol here means the average value. So the bar over the x marks the average. And as I said before, this is the formula. Basically, we add up all the values and then divide by the amount of values we added together. So here we have 5 values, add them together and we get 40. We divide by 5, because 5 values, and we get 8. So the mean, or the arithmetic average of this data set, is 8. Unfortunately, average can be deceiving. Just with the average, you would normally assume most numbers were around 8, and that's why there's 2 more measures. With median, we look at the middle value when ordered in ascending order. Now with 5 values, the third is in the middle, so median is 6. Now you may be wondering what if there were even numbers like 6 or 8 measurements. Well, you find the 2 middle values, so let's say we only had 4, 5, 6, and 12. Our 2 middle values would be 5 and 6, so we would take the average of that, which is 5.5. Here we have an odd number of them, so it's just the middle value. We see that it's lower than the average is, so we know that there are more values that are lower than the average, but the values that are higher are most likely further away from it than the low ones are. And we can't know for sure, that's why we have our third measure, which doesn't fully solve this, but it does help, and that is mode or frequency. So if we look at our set, we see that all numbers appear exactly once, so there is no mode, or all numbers are the mode. It depends on your teacher, really. Our teacher said if there's max 3 different values that repeat the most, so let's say I said of 2, 3, 3, 3, 4, 4, 4, 5, 5, 5, and 6, we can set the mode as 3, 4, and 5. If there would be 2 more 6s, so we would have 2, 3, 3, 3, 4, 4, 4, 5, 5, 5, 6, 6, 6, we would say that there is no mode. Sure, it may not be the correct way, but it was done to simplify the process for us because we were like 15, no, maybe less. But yes, I say that it's best if you write all of them, so all that appear the most often. And by most often, I mean compare the n of each value and write out only the value with the highest n, or more values if there's more. In our example, we would have the comparison as follows: 1, 1, 1, 1, 1, since all appear the same amount of times. But if we had like 4, 5, 6, 6, 12, 13, we would have a comparison of n's as 1, 1, 2, 1, 1, and 6 would be the mode. Here, all appear once, so there is no mode. There is another name for the median. It is the second quartile. This name implies the existence of at least two more, the first and the third, because quartile is something to do with 4, which, if we go by how median is defined, we can assume that they are the 1/4th value and the 3/4th value. So left and right half of the half point. Don't worry, there's a nice image that shows this very well in a little bit. Before that, we need to know what spread of data is. It describes how wide the data is, quote unquote, of course. Another word could also be range, and that you get that by subtracting the minimum value from the maximum value, like so. Now, as promised, here's the image that also shows this. We have data of not all values between 24 and 57. Our range here would be 57 minus 24, which is 33. Median, or the second quartile, is the middle value here, so the average between the two around the center. That is 36, because we have an even count of numbers. After that, we take the look at the values left of the blue line, so the first half of the data. Since it's even again, we take the average between the two middle numbers, giving us 26.5 for first quartile. And the same story for the right side, or the third quartile, giving us average between 50 and 52, which is 51. Why is this useful? Well, the amount of data between the first and the third quartile is half. Or in other words, interquartile range, or IQR, is the data between the first and the third quartile, and it represents exactly half the data. Well, in even systems like this, it does. In odd, it may be slightly less, since we don't count any quartiles when determining others. So if we had only 24 to 40, so this red line determines the end of the set, so only the left part is the set, then we would have 27 as the second quartile, 25th as the first, and 32 as the third. Our IQR would be 3, since 1, 2, 3 numbers are between the first and the third quartile. But all the numbers here, if we count them out, are 7, so slightly less than half, but that's about it on the topic for me. I'm not gonna go into complications. Basically, about half the data is between the first and the third quartile, and yeah, that's mostly what this data is all about. Now, because this is more important, variance and after it deviation, I won't dive too deep into the previous topic, just this one, so all I want you to know is the average, like the mean, because that's the most useful statistical analysis for most people in their everyday life. Sure, the most appearing number, the most frequent number is also common, but the average is most likely what you work with in real life. So, but yes, variance and deviation, they basically tell us how far our values deviate from the average, but this is more important if you're doing parallel measures, like in chemistry with 3 solutions prepared to be the same concentration, and then you measure and you have 3 different answers. Deviation would tell us that the average difference between each measurement and the average of all measurements. So how much it deviates from the average. We have 2 types of variance. One is sample variance and the other is population variance. As the name suggests, population variance is the one that is used on bigger amounts of values or counts, more representative to the system, while sample variance is the one used for smaller systems like the example for chemistry I mentioned. To be fair, maybe another example would be better, like dropping an egg from the table and measuring it 3 times, or whatever. So in high school, our teacher showed us a simple way to do this. He said you write out all the measurements, you calculate the mean, or the average, then calculate the difference of each measurement towards the average, and write them next to the measurements. After that, you cross out the 1/3, like a third of the greatest differences, aka the biggest difference from the average. After that, you take the average of the differences that are left, and that would be the deviation. This is a severe oversimplification, and I'll show you step by step after I finish describing it, but it is important to know that this comes from a concept we will show a bit later called Gaussian distribution. So let's solve this the way our teacher showed us. I add these numbers together and divide by 5, and we get the average of 1.538 seconds. So I'll round it up to 2 decimals, just like all the results here are. Next, I'll write the difference between the average and the average and the time. I'll mark the difference with AD. Plus or minus here does not matter, as we're looking for the third that are the furthest away from 0. And 1/3 of 5 is 1.66, which if we round up, it's 2, just for simplicity, meaning we'll cross two greatest differences out. In this case, this is 0.08 and 0.1. Now we take the remaining differences, and we get their mean value, or the average, and that will be our deviation. So 0.04 plus 0.02 plus 0.03 divided by 3 is 0.03. Or at least it was something like this. Since you're listening to me, I'll show you the real method, the one that the big kids use. But yeah, this would be how our teacher taught us in primary or high school. But now at university level, we actually work with formulas. Like this. It's these two, which we will now get to the formulas, of course. Population variance is labeled with lowercase sigma squared and equals to the sum of squares of all the differences. That's why the signs plus or minus didn't matter. And you take the differences we had before and you square them to get rid of the minus sign, of course, and then add together all the squares. After that, you divide by the amount of the differences that you had and you get the population variance, or sigma squared. The Greek letter here in the bracket next to x is mu, which in physics is used as a symbol in units, meaning micro. Here it refers to the true average of the population. Well, I think it's the right translation for it at least. As for the sample variance, the more used one in everyday situations or chemistry lab, has the same formula except for a few small changes. Here instead of sigma we have s, instead of mu we have x average, and instead of n we have n minus 1. Why? Well, to be honest, I don't have a clue. Our unit teacher said it has something to do with spatial stages or something like that, but I think it's just a correction for the fact that it accounts for a smaller sample, like smaller sample sizes are less precise. So the variance must be greater to accommodate for that, because if I measure 5 times, and the deviation from the average is going to be huge. But if I measure 1,000,000 times the same measurement, the values are going to be moved more towards the average. Of course, there are going to be some that are going to stick out, but they're going to have much less weight compared to the ones that are close, because like percentage-wise, we will see this in Gaussian distribution, there's going to be a lot more data closer to the average than the ones spread afar. So the weight of individual difference is going to be much less than it is in a smaller sample. So that's why we divide by a smaller number, so that the variance is bigger, meaning less precise. But this value is still squared. So it doesn't represent the actual difference from the average, and that's where deviation comes from. Deviation is basically a root of variance. Now, this is finally our measure for how far typical points lie from the mean. And whenever you have this deviation given, or you have to solve for it, you give your result in such form. So deviation is this, and this is the average value. You must remember that both of these have the same unit, so don't forget to write them down. But yes, this means that if variance is 9, the standard deviation is 3. And then you just have the value of this, like the result you're calculating for like time, is the average measurement, like the average of all the measurements, plus minus deviation. Now you can write a bracket and both numbers in, and then end bracket and add the unit, or you just have number unit plus minus number unit. Whichever you prefer, just make sure you don't forget the units. Now for the relative standard deviation, this is a percentage value representing what percentage does the deviation represent compared to the average value. So how much does the deviation represent? What part of the value of the average does the deviation represent? For instance, if we have a measurement at 10 seconds, deviation of 1 second and deviation of 5 seconds obviously don't represent the same part. 1 second is about 10% and 5 seconds is 50%. Yeah. So how would we describe that? With relative standard deviation. So we divide the standard deviation with the average value and multiply it by 100% to get RSD. Or if you want to write the result with this relative standard deviation, you just have the average, bracket 1 plus minus, standard deviation divided by the average. Why? Because if you remember this formula here, x average plus minus standard deviation, we can factor out the mean, so the x average, from it, and we're left with the mean times the bracket from which we isolated it, and then mean divided by mean is 1, plus minus standard deviation divided by the mean. So this is how we get the formula. And this represents the decimal writing of the percentages. So yeah, essentially this plus minus how many percentages of it are deviating. I overcomplicated this for a lot. But yes, we'll use this to be able to calculate with values that have errors accounted for, like this. So our rule is that the deviation of the result, marked as delta R, so deviation of result, because delta means a change, is equal to the square root of the squares of all deviations. Some teachers simplify it into the deviation of just being a sum of all deviations, but this formula is just slightly more correct. So when you're adding or subtracting values with errors, you have to take their standard deviation, so the S, square each of them, add them together. Even if you're subtracting, you have to add the errors because mistakes add up on every step you do. And after that, you square root of it, of course. But yes, let's solve this example. We have our A value with 12.4 plus minus 0.2 and a B value of 3.1 plus minus 0.1. Our goal is to calculate the average R, or whatever the R is here. Our goal is to calculate R, where R is defined as A minus B. So basically take the difference. So for the difference, or the base value, we're gonna take the difference between the main values here, so the averages of them, because we're assuming that these are the average values of A measurements. So A measurement of 12.4, 12.6, 12.2, etc. So we just calculate between the average, and we get that the average value, I guess that's why I put the line there, of result is 9.3. Now, let's solve for the mistake or the deviation. So delta A, or the deviation of it, is 0.2, and delta B is 0.1. We square again, so we square each of them, and then add them together, then take the root of that. So square this plus square of this is, and when rooted is 0.22. Now, a good practice we have in our classes is that you take the second significant figure of the deviation and you round it to the first, essentially having only one significant figure in it. I'll tell you more about it in a bit. In this case, this would give us 0.2. Next, we take the result, which is 9.3, and round it to the same place, decimal place, or whatever other it was, that deviation has its significant figure at. So here our result 9.3 only has one decimal place, and our deviation has its significant figure there. We don't need to round anything. We just write the result as being 9.3 plus minus 0.2. Of course, in school, if the teacher explained like adding up the mistakes, you would have plus minus 0.3. But entirely correct, it would be this, or maybe even this. Yeah. Depends on if you have to account for significant figures. If it's not directly specified or demanded from you, like that you know you have to follow the rules, I think it's safe to just have 3 of them, so the maximum of 3 numbers, so 0.385 or 228, because 3 is not a lot, but it's also not like nothing. It's precise enough to be able to differentiate between 1,000 different values, if that makes sense. But yes. Okay, next is multiplication and division. For this, we have to know, like, for the rule of it, is what multiplication is, and we know that it is an addition of a value to itself n times. So the error will be squared, and then it will be multiplied n times, and then taken a root of. But that n also has its own error. So here is where our relative standard deviation comes in. The percentages allow us to just add them together, sort of. The ratio of the deviation to the result, so the plus minus part divided by the whole part, like 0.2 divided by 12.4, for instance, on the previous example, is equal to the sum of the squares of deviations to their respective values. So here we basically add the squares of relative deviation in decimal form, and then we take the root of it, and we get the RSD for the result, in the decimal writing, of course. And if we want the deviation, so just S, we multiply it with the mean, which we calculate by simply dividing or multiplying the means of components as usual. So for the example, because I'm slightly sick and I'm overcomplicating everything, we have A being 4.0 plus minus 0.2, b, 2.0 plus minus 0.1, and r, which is 8 times b. So if we multiply the base values, we get 8. Why do we keep the decimal point there? I'll explain this after this slide, I think. Sorry, after this example solved. Yes. What about the error of the result? Because it's not very precise. Well, here's the formula that I copy out. Now we insert the values. 0.2 goes on top, 4 goes on bottom, 0.1 goes on top, 2 goes on bottom. We get in, we square, we solve, we take a root of, and we get 0.0707 in the percentages values. So that's like 7.1% relative standard deviation. And then we multiply this with 8, and we get 0.5657, and we round this to our one significant figure, so 0.6, and we have a result of 8.0 plus minus 0.6. Technically, we could just convert these to percentages by dividing and then like working with that, but why not? We could also leave the percentage like this, and we would just have 8 bracket 1 plus minus 0.0707, end of bracket, and then the unit. But yes, this is also another way of writing the result, because standard deviation is just the preferred way in many examples. Now, there are rules for exponentiation, logarithmization, because of course they are. But I won't bother you with them, as this video could easily be split into 4. Plus, they get more and more advanced, and now, as I promised, significant figures. So what are significant figures, or sig figs for short? First point is that they're all non-zero digits. So 1, 2, 3, 4, 5, 6, 7, 8, 9. These are the non-zero digits. Next, we have 3 rules for zeros. The first possible is that zeros are between other digits, like here, where we have an example of 1.2037. This is 5 significant figures. Why? Because we look at the first and the last digit, and then all between are significant figures. And we just count them. That's it. That's as easy as it is. Look at the first and the last digit that are not 0, and then add the count together. Next is that a 0 is a leading digit, like in number 0.0000123. Here are 3 sig figs, because none of the zeros before this are significant. Technically, we could multiply this by 10 to the power of 5 and have 1.23 times 10 to the power of 5. So these are not significant. No matter how many there are here in front, as long as there's no other digit in front of them, they are non-significant. And lastly is trailing zeros, where zeros follow other digits. Here we have another split. First option is that the zeros are in the decimal place, like here. In 1.200 or 120.0, we both have 4 sig figs, because if it's in the decimal place, it is significant. Because the more decimal places you have defined, think of it this way. When you have a whole number, you write it out all the way to 0, so like the decimal comma, decimal point, whatever. So 1200 cannot, like, sure, you can write it as 12 times 10 to the power of 3. I think that's the one I gave an example. And that gets rid of the zeros. But those digits the places will always be there. So 1200 decimal comma, and there's no decimals after it. Those zeros before on the left of the decimal comma will always be there, or at least some digit will take their place. However, the decimal places are not always written. So if they are written, they are significant. I hope you see the way that what I'm trying to explain, because I genuinely don't know how to translate this into English without sounding crazy. But yes, if you have a decimal place written, it is a significant one. Unless it's like in the previous example with leading zeros, these are not significant because they're in front of the set. Hopefully this kind of makes sense. But yes, for the not significant if no decimals, so like lastly, when the zeros following are not decimal, like in 1200, like I said before, here we have only 2 significant figures, because, well, the rest are not precise, like we just rounded up to 2, and the rest becomes 0, kind of. But yeah, hopefully this is a good rundown of what sig figs are, so we can continue on how we determine how many we need in our results, based on the amount of them in the numbers we work with. How to know what the significant figure is when measuring? Usually you look at the last digit. So let's say a stopwatch measures full seconds. If you make a few measurements, you add them together. Take the average, whatever it may be. It wouldn't make sense that the result you get has 3 decimal spots because that's a lot more precise than your instrument allows you to. So to recap, you have no decimal spots in the measurement on the stopwatch, but your result would have 3 decimal spots because that's the average. It doesn't make sense, because it's like a lot more significant figures than you actually measured. That's why there are a few rules, so let's check them out. Let's see how to determine the amount of significant figures when calculating. I may or may not follow these rules in the future, but they are set so you don't have a result that is more precise than measurements, as I said before. So let's start with multiplication and division. The rule here is that the sig figs of the result will be equal to the lowest number of sig figs from inputs. So let's say on our example, we multiply 2.44 times 1.2. Our first input has 3 sig figs and the second has 2. The result will have 2 sig figs because 2 is the lowest count. So long story short, the precision of the result is limited and set by the precision of the least precise input. A lot of precision here. So even a product of 0.12121212121212 times 2 will only be 0.2 with only 1 sig fig. If 2 was given as 2.0, it would be 2 sig figs, making the result 0.24. I hope this was clear enough, because this measurement here is limiting the precision of our answer. Addition and subtraction are slightly different, but not quite. Unlike with multiplication where the least sig figs mattered, here the least decimal places do. So it's basically the same formula as before, except we looked at the decimal places instead of sig figs. Although more often than not, the number with least decimal spaces is the one with least sig figs. So in our little example here, although we have 5 sig figs plus 1 sig fig, the result is 3 sig figs. Now this is just a coincidence that the number is the average of the two, but still, if we look at the decimal place, so 3 decimal places and 1 decimal place, the result is 1 decimal place. There are other rules like for roots, logarithms, etc., but I won't bother you with them again, because if you really want to know, you can literally Google sig fig rules, and you'll get a lot of easy to read materials. Now let's just learn how to round numbers, just in case some of you may have issues with that. When you take a number and you have to round it, like to the first decimal place, you take the immediate number in the place after the one you're rounding to, checking a few conditions, then changing the selected place accordingly. So if we have 1.234 and we round it to the first decimal place, so towards the 2, we check the next decimal place, which is a 3. This is rounded down, so the result would be 1.2. Why? The first rule is whether the next place is greater than or lower than 5. So if the number is less than 5, like 3, you round down. But if it's greater than 5, you round up. What if it's exactly 5? Some teachers say always round up, some say always round down, some say choose whatever you want to. Well, our teachers showed us this amazing thing called Banker's rounding rule. It states that if the digit is 5, you look at what's after it. If there is anything at all, even if it's 100 zeros followed by a 1, as long as it's greater than exactly 5, you round up. But if there is nothing, or like a few zeros trailing it, you check the number you're rounding to. Here are 3 examples. We want to round the whole numbers. 17 has a 5 in the next place, so we see if there's anything after it that would make it greater than just 5. We see that there isn't. Even if it was written as 17.50, it would be the same as this one, for rounding purposes. And if there isn't, so this is exactly 5, we check the number in front of it, like I said, but I didn't finish speaking because I forgot. We will round to the even number, always. So if it's exactly 0.5, or the 5 is the number you're rounding to something, and there's nothing after it, you round to the even number. So in this case, the even number around this 17.5 is 18. Now we have 14.500001, and we have this 5 again, and now we check if there's anything after it. It is. It's 4 zeros and a 1. That's just enough for the value to be higher than exactly 0.5, which rounds it up to 15. And lastly, we have 28.5. We see there is nothing after the 5, so we will round to the even number. So between 28 and 29, we choose 28 because that is the even number of the pair. With this, we finish the things everyone must know, and we're moving to the things that everyone should at least be familiar with. I will first list the distribution types, and then I will go into deep depth for the Gaussian one, because it's the most common one, most likely to encounter in your life. It appears in situations like exam point distribution, IQ points of populations, etc. Second is skewed distribution. It's more common in reaction time measurements, contamination levels, where you know that there is going to be one thing that's going to be peaked, but then it tunes out. So like reaction time, most people average on the low end, but due to several factors that can influence it, it's going to go stretch out to the higher values. Contamination level, usually it's low, but it can also stretch into both ways. And last is the uniform distribution one, which is prevalent in random generators or dice simulators. Here are a few other distribution types. We won't really go into them. There's the formulas if you really want to know them. Oh, I forgot the Gaussian formula. It's not that important. We're gonna run into it in physics at least, so don't worry. But yes, Gaussian distribution is a curve with a perfect property to help us analyze data. We put the mean in the center, like shown in the left picture. Then the sigma symbol shows the standard deviations, so one standard deviation from the mean out contains 68% of all data, so of course one standard deviation in both ways. This is roughly 2/3, which explains why back then when we crossed 1/3 of the deviations that were the biggest, now we know that this is because they were outside of this big one deviation part. Now, if we add one more standard deviation in both directions, we suddenly have 13.6% more per side, which results in 95% of all data. And if we want to be statistically safe by counting out all the outliers, or data that is significantly different from the mean, we take the 3 standard deviations marked with +3 sigma and -3 sigma, and they contain 97.5, so that's a lot. Oh yeah, I did the math here. This is 68, and then you add 2 times 13.6, yeah, that's exactly 95. Yeah, and the right one shows the percentages as well, and color codes them, so this is also very nice. So let's say we have an example, a set of data with a Gaussian distribution has a mean of 50 and a standard deviation of 5. We need to determine how much data is present within the range of one standard deviation, so between the value of minus deviation plus deviation. In our case, mean minus deviation is 45 and mean plus deviation is 55. So the amount of data with values between 45 and 55 corresponds to the 1 sigma shift from the mean on the image given. Since 5 is the standard deviation, and we only took one value, this is 1 sigma deviation, so all that data is 34.1 in one direction and 34.1 in the other, giving us 68.2 or just 68% is fine. Now, if we wanted to know in what range we would find the 99.7% of all data, we would look at the image and see that that percentage that adds up to 99.7 comes from -3 to +3 sigma, meaning that if you manually add up all the pockets here, you don't get 7 on the decimal place in 99.7 because these are rounded numbers, so we lose the information. But if we do look at the -3 + 3 deviation, 3 times standard deviation is 15, so 50 minus 15 is 35 at the bottom part, and 50 plus 15 is 65 for the top part. So we see that this isn't hard at all. Well, technically we use this for actual tests. I will mention them, but I won't give you the formulas as per recommendation of my brother, so I don't overload you with information. But if you're interested in the topics, you can keep digging, and if you aren't, you're not gonna get overloaded with information, as this video is already very packed with different topics on this, with different pieces of information on the same topic. Now, you may have heard me use the word precise a lot today. That's because it doesn't actually mean the same thing as accurate. The best way to show it would be on this image. Up first on the left, we have an accurate and precise shooter. We see that they hit the center of the target with a very low spread. Another word for both of these together could also be correct. Second, we have a precise shooter that wasn't accurate. We see that they didn't hit the center, but the spread was very low. So we see that precision is used in the context of standard deviation, and accuracy in context of closeness to the mean or the average. The third and fourth image reaffirm this. On third, we see that the average position of the points is roughly on the center, but the spread is horrible, so it's accurate, however not precise. And fourth has a horrible spread, and it's nowhere close to the center, so it's not accurate nor precise. So how could I remember this? Well, accurate and average both start with A, and precision and deviation both have ion at the end. So hopefully this helps you. And last topic we cover are errors. We have two types of errors. First are systematic errors. As the name suggests, they are the one that happen systematically or by a system. How? Well, there's many reasons. It could be poor calibration, something messing with the device. And how do we notice this? All data has a shift, so it is inaccurate. But it can still be precise, because it's mechanically measured. That's why chemistry does standardization. You measure a standard to see if the response from the device is the same as the standard should give off. If not, you know the device needs recalibration, or you know how to correct the measurements. As it's usually in one or other way, so either lower or higher values than should be given. So usually systematic errors are always moved from the average in the same direction. So always slightly heavier when weighted, always, or lighter, but you can't have systematic error if you measure the same weight and once it gives a higher and the other times it gives a slower result. And the second error are random errors. They come from stuff like misreading a number, shaking hands when measuring, or loss of sample when carrying it. The results are not very precise, but they are hopefully accurate. Now, errors cause deviation or move of center. But how do we know if a measurement is still acceptable for the set, or if it's an outlier and shouldn't be accounted in the average and standard deviation calculations? That's where statistical tests come in. There are a lot of statistical tests. I wanted to cover a few of them and their formulas, but I was like, you know what, this video is already packed like over 40 minutes of stuff, so I'm just gonna list them and you can Google them if you're really interested, because they're not really that common in everyday situations. But yes, the first one I listed here is to determine, so the student's t-test determines whether a difference between responses or means of two groups are statistically significant or not. Basically, if we can say that the two groups can be grouped into one or not. The following two, the Q-test and the Grubbs test, are the outlier tests. They're used to determine whether a data point is an error significantly too far away. Usually you run this once to get rid of the one outlier that is the biggest deviation away from the center. And just to name a few more, like F-test, Z-test, there's a lot of them. Even just checking the Wikipedia page titled List of Statistical Tests, it will give you enough material to read for a week. Or cry for a week, whichever you prefer. Now, there's a lot more that I could cover, maybe some stuff that I should cover, but I know that with these basics you will be able to understand most of the things that you come across in life or in my lessons/lectures. So here is the mini test. I wish you the best of luck. I did try and make it easy and to account for what we covered and not make it too hard. Anyway, thank you very much for tuning to today's lecture. I hope you learned something new. I hope everything went well. And I'll see you all on our next quest. Bye!